to the afternoon session. Before we even start, let me remind you that today is the last day to register for the social dinner. So maybe at coffee break, you want to go to room 208, I believe, to pay for the dinner if you're interested. And let's begin. I'm very happy to introduce Juan Carlos Mongez.
Yes.
Okay. And the title of his talk is Measure of Maximal Entropy for Partially Hyperbolic Diffeomorphisms with One-Dimensional Center.
Thank you. So I would like to start by thanking the organizer for the opportunity to speak here today about my work. This is a joint work with Maria José Pacifico, and in this research we have found an open set of partially hyperbolic diffeomorphisms with one-dimensional central bundle that admit just a finite number of measures of maximal entropy. So as introduction, let's recall what a measure of maximal entropy is. So in dynamic, we often speak about two types of entropy, the topological entropy and the metric entropy. The metric entropy is related with an invariant measure. So the rational principle states that the topological entropy of a continuous map is equal to the supremum of the metric entropies over the invariant measures or just the ergodic ones. So a measure that achieves the supremum is called a measure of maximal entropy. These measures are important because they capture all the complexity of the system, helping us to better understand our dynamic. So these measures are tools to study our dynamic. And if we want to study our dynamic using these measures, the first question that we need to ask is whether these measures actually exist. So a natural question arises, does a diffeomorphism have measure of maximal entropy? And when these measures exist, the other natural question is how many are there? When the number is finite, it's easier to study each one or choose one to focus on. So if we want to answer this question for diffeomorphisms, we can start looking at the hyperbolic diffeomorphisms because these diffeomorphisms are well understood. So an invariant compact set is a hyperbolic set if we have a splitting in two directions, the stable direction where we see a uniform contraction under our derivative, and the unstable direction where we see uniform expansion under our derivative. So when the non-boundary set is equal to the closure of the periodic points, and this set is a hyperbolic set, we say that F is an option A. And when M is a hyperbolic set, I mean the manifold, we say that F is an anosov diffeomorphism. Okay, so what do we know about hyperbolicity? Well, in the 70s, Margulis, Isaia, and Bowen studied these questions for hyperbolic diffeomorphisms, and now we know that anosov and option A has a finite number of measures of maximal entropy, and when the anosov is a transitive diffeomorphism, we know that it just have a unique measure of maximal entropy. In the case of anosov diffeomorphisms, the topological entropy is a continuous function when we vary the diffeomorphism. And the number of measures of maximal entropies is a constant function too. So in this context, we have a general answer. We know that measure of maximal entropy always exists, and we know that the number of them is finite. We can be optimistic and try to find a general answer for general diffeomorphisms. Newhouse proved that for, say, C-infinite diffeomorphisms always exists measure of maximal entropy. And recently, Busi-Krovitzer and Zarigi proved that when this manifold is a surface, the number of measures of maximal entropy is finite. When we look at higher dimension, this is not true. It's easy to take example. For example, node of times a rational rotation. If we are going to find an infinite an infinite number of measures of maximal entropy. And when our diffeomorphism is just here, but not infinite, we can find example with any measure of maximal entropy. So in this context, in general diffeomorphisms, we don't have with general answers. Sometimes we have measure of maximal entropy, sometimes we don't have, and the number varies, depends of the diffeomorphism. So to try to find a concept where we have a general answer, we can come back to the hyperbolic diffeomorphisms, to the Anosov diffeomorphisms, and look at the partially hyperbolic diffeomorphisms that are a natural generalization of the Anosov diffeomorphism. But in this time, our splitting has 3 directions. We still have the stable direction and the unstable direction, but now we have an intermediate direction where we don't see more contraction than the stable direction, and we don't see more expansion than the unstable direction. We are going to focus on in partially hyperbolic diffeomorphisms with one-dimensional center. These diffeomorphisms always have a measure of maximal entropy because they are entropy expansive. So we are working in partially hyperbolic diffeomorphisms. In other hand, we know that the topological entropy is calculated by counting the number of n epsilon separated points. The problem with this definition is that this definition is quite topological. If we want to use the tools that we had in the case of hyperbolic diffeomorphisms, we need an alternative definition more close to the structure of the hyperbolic diffeomorphisms or the Anosov diffeomorphism. So we know that in the case of Anosov diffeomorphisms, partially hyperbolic diffeomorphism, we have an unstable folation, we have unstable manifolds, and we can see how points are separated by the iteration of our dynamic. So in these unstable manifolds, we can find entropy. And this is the idea, this is the motivation behind the unstable entropy. So to define unstable entropy, we can use our Riemannian structure to define a metric along the unstable manifold, each unstable manifold. And so we can define n epsilon separated points. And we can proceed as in the case of topological entropy. And so we are going to define a metric entropy for each unstable manifold. And in the end, we are going to take the supremum of this number. This is the idea to define how to define the unstable entropy. There are some technical issues, but this is the general idea. Here is the formal definition. OK, so if we want to define the stable entropy, we know that when we have a partially hyperbolic diffeomorphism and we take F inverse, the unstable direction becomes the unstable direction. So we can define the unstable entropy as the stable entropy as the unstable entropy of F inverse. And this is a good definition in the case of Anosov diffeomorphisms because this is an alternative definition for the topological entropy. I mean, the topological entropy is equal to the unstable entropy and equal to the stable entropy in the case of Anosov diffeomorphism. We also can define unstable metric entropy. I don't want to spend much time here, but the idea is to use a special type of partitions that are called increasing and subordinated to the unstable folation. And this partition has some properties that are related to the unstable folation. Using these partitions, we can define the unstable metric entropy. And this definition does not depend on the choice of the partition. So in the case of partially hyperbolic diffeomorphisms, the unstable entropy and the stable entropy are not an alternative definition for the topological entropy. Sometimes we can have a topological entropy different from the the unstable entropy. But we are going to use this definition because this definition has very useful properties to work. For example, we have a variational principle, but in this case, measure of maximal unstable entropy always exists. This not happening in general context. Okay, so now we can state our main theorem. So our setting is a partially hyperbolic diffeomorphism C1 plus with one-dimensional center. So if the unstable entropy is greater than the stable entropy, our diffeomorphism has just a finite number of measures of maximal entropy. When we have the other inequality, we have the same, we have also a finite number of measures of maximal entropy. We just need to apply our theorem to F inverse. So when we have the unstable entropy different from the stable entropy, we have a finite number of measures of maximal entropy. And I told you that in the case of an also of diffeomorphisms, the topological entropy is a constant function when we vary the diffeomorphism. In our case, we can prove that for C1 plus diffeomorphisms close enough to F, the number of measures of maximal entropy of G is at most the same number of measures of maximal entropy of F. This implies that when F has just one measure of maximal entropy, G has also one measure of maximal entropy, so the uniqueness is an open property in our set. Okay, so in the rest of my talk, we are going to see a proof for the first part of our theorem. The second part is a little more technical, so we are going just to prove the first part. So to prove this theorem, we used the Bucy-Krovitsier-Zarigi criterion. This is a new criterion that is very useful to counting the number of measures of maximal entropy. So to introduce this theorem, we need to recall what a hyperbolic measure is. So a hyperbolic measure is an ergodic measure such that all its Lyapunov exponents are different from 0. When we have a partially hyperbolic diffeomorphism with one-dimensional center, a measure is hyperbolic if the Lyapunov, the central Lyapunov exponent is different from 0. Okay. So these measures, the hyperbolic measures, are important because we know by Pessin theory that almost every point has invariant measures. The problem with these manifolds. The problem with these manifolds is that we don't have a control over the size of these manifolds. I mean that we can have points so close and we cannot guarantee the transversal intersection between the manifolds. So this is a problem in this case. But using these measures, these manifolds, and these hyperbolic measures, we can define, as we did in the case of hyperbolic periodic points, and define homoclinic classes for hyperbolic measures. Two hyperbolic periodic points are homoclinically related if there is a transversal intersection between the invariant manifold of them. In the case of hyperbolic measures, we are going to require the transversal intersection between manifold of points into sets with positive measure. So we have two measures, two hyperbolic measures, and we need two sets. One set for this lambda. So we have here a set, and we have other sets. This set has positive measure for mu1, and the stable manifold of them have to intersect transversally the unstable manifold of this set. This set has positive measure for mu2. So we need something like that, and we need the other intersection, maybe with other sets. Okay, so and the homoclinic classic of a hyperbolic measure is the set of all the hyperbolic measures that are homoclinically related to it. Okay, this relation is an equivalence relation, so we have a partition of the set of hyperbolic measures. Okay, the Bussy-Crobesier-Sarigi criterion established that each homoclinic class has at most one measure of maximal entropy. And as a corollary, we have that hyperbolic measure of maximal entropy cannot be related. So the strategy to prove our theorem, it will be to think by contradiction that we have an infinite number of measures of maximal entropy. And we are going to try to find transversal intersection between some manifolds, some manifolds of maximal entropy, measure of maximal entropy. But this strategy has two problems. The first problem, as I told you, is that we don't have a uniform control over the size of the manifolds. And the other problem is that the Bussy-Crobesier-Sarigi criterion, if we use this term, we don't have information. We have information here. These are the ergodic measures. Here we have, in this part, we have the hyperbolic measures. And here we have the the non-hyperbolic measure. So here we have a partition, maybe an infinite homoclinic classic. But here we have a partition, but here we don't have information using this theorem. So this is the other problem. We have two problems. The size of our manifolds, we don't have information about measures of maximal entropy that are not hyperbolic. So to solve this problem, we are going to explore some consequence from our hypothesis. So here we have three consequences. The first one says that our hypothesis is an open property. So when we have f as in our theorem, there is a neighborhood such that each diffeomorphism in this holds that the unstable entropy is greater than the stable entropy. So our property is an open property. The second consequence is that each measure with high entropy is a hyperbolic measure. And the central Lyapunov exponent is far from 0. And this is very good because we can apply things like the Please lemma or this type of tools. So, and the last one, in the case of unobserved diffeomorphisms, we know that the topological entropy is is locally a constant function. In this case, we can prove that the topological entropy is a continuous function. So the item 2, the second consequence, solves this problem because this says that we don't have measures of maximal entropy here. Each measure with high entropy is a hyperbolic measure. So this set is the important set. Okay. Okay. And now we need to solve the other problem, the problem with the size of our manifolds. So first, we defined the hyperbolic time. We can define a set where we have a uniform size for our invariant manifolds. Yes, for the invariant manifolds points into these sets. The problem with this is very good because we have a control. When points are delta close, we can guarantee the transversal intersection between their manifolds. But the problem is that maybe this set is not relevant for some measure of maximal entropy. So using a Bliss lemma, we can prove that for each measures with high entropy, in particular measure of maximal entropy, this set have positive measures, and this is we have a uniform control over these measures. And this property, this beta, I think that is yes, this beta, helping us to prove the second part of our theorem. So now we solve our problems. We can prove the first part of our theorem. So just to recall, we are going to prove that in our setting, when the unstable entropy is greater than the stable entropy, F supports just a finite number of measures of maximal entropy. And as a corollary, we are going to prove, because our hypothesis is an open property, we are going to prove that in a neighborhood, each diffeomorphism has a finite number of measures of maximal entropy. The problem with this corollary is that we don't have a control over the number of measures of maximal entropy of G. So maybe F has just one measure of maximal entropy, but the other diffeomorphism has a lot of measures of maximal entropy. Okay, so to prove our theorem, we first are going to associate a good set for each measure of maximal entropy. So we are going to take a measure of maximal entropy, and we are going to take our hyperbolic time, our set where we have manifolds with uniform size. So we know that the measure of this set is positive using this measure of maximal entropy. And so we can take a point in the support of mu such that this is true. This one. We define this set. So for each measure of maximal entropy, so measure of maximal entropy of F, we are going to associate a set. And note that this set has so important property. For example, the measure of this set is positive. You can see there. The diameter of this set is a small diameter, and in this set, the points there has manifolds with uniform size. So now we are going to suppose by contradiction that we have an infinite number of measures of maximal entropy. And so we are going to choose, we are going to take a set for each measure of maximal entropy like this. And by compactness, in a moment, we are going to have two sets that are delta closed. So as we have uniform, we have something like that. We have here our hyperbolic type, and we have here our lambda mu, and we have the other one close to them. And here we can guarantee the transversal intersection between the manifolds, because in this set we have uniform size for the manifold. And we know that this set has positive measures, so we have proved that these measures of maximal entropy are homoclinically related. And this implies that this implies we have a contradiction of the Boussy-Krovitz-Sarygin theorem, and this implies that the number of measures of maximal entropy is a finite number. And this proves our theorem. It's important to note that we just need that the Lyapunov exponent for measure of maximal entropy, we need that they are far from 0. With that is enough to prove our theorem. And this is all. Thank you.